Electrostatics. We're going to keep the electricity and magnetism section of this course pretty high level. We've done a lot of work at this point and taken a lot of care to deeply cover the mechanical topics along the way. And we are approaching the end of the course, so these last few topics are not worth quite as much of your attention as the ones that we've covered already. But of course, we want engineers to be well-rounded, so we have to at least hit the high points. So let's start by talking about electrical charges. We can have positively or negatively charged particles. The negatively charged particle is the electron, and one electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. Coulombs are the unit of electrical charge, and a proton would have the same magnitude, but it would be positive instead of negative. And when we have a charged particle, it creates an electric field around it. So for instance, let's imagine that we had a positively charged particle, and then we were to introduce another positively charged particle in the vicinity of that proton. Then like charges would repel, so there would be this electric field, and we can draw these field lines in every direction away from that positive charge that indicate that the introduced positive charge would be repelled. If, on the other hand, we were to introduce a negative charge in the vicinity of this, the field lines would look the same, but the arrows would point in the other direction because they would attract instead of repel. And the electric field gets the variable E, and it has the units of newtons per coulomb. So that's units of work or energy per unit charge. Or it can also have the units of volts per meter. So that's potential difference per unit length. And those turn out to be the same units, and you can show that. But for now, just take my word for it. And we can calculate the force that's exerted on a particle that's introduced into an electric field as being a function of two things: the charge of that particle that we're introducing, Q, and the field that we're introducing it into, E. And we can see that this will work just based on the units. The force is going to have units of newtons, that's what we're looking for. And the charge of the particle being introduced will have units of coulombs. And the field has units of newtons per coulomb. So coulombs will cancel and we'll get newtons. And if we don't know the field strength, we can still calculate the force based on the charges of both particles if we know them. And this is Coulomb's law. This is a very popular and frequently tested formula that will come up. The force equals Q1 times Q2, so the product of the magnitude of the two charges, over 4 pi times epsilon times r squared, where epsilon is the permittivity, because an electric field strength depends on the medium in which that field exists. So if it's air, then there'll be a certain permittivity to air, or if you're in a vacuum, it'll be the permittivity of free space, and that's a value that you can find in the reference handbook. But you could also be in a different medium, and different mediums will have different permittivity, which will affect the field that's created by a given charge. R is the distance between the 2 point charges. So if you know the magnitude of both charges, the distance between them, and the permittivity, then you can find the force between those two charges. And the only other thing to notice there is whether that result turns out to be positive or negative. If that result turns out to be positive, that means that those two charges are the same, so they're going to repel. And that's the case if they're both positive or both negative. If, on the other hand, one is positive and one is negative, then this result will be negative, and those 2 point charges will attract. So it's pretty intuitive. I think in the reference handbook, they show this with a vector at the end, and I think it's just another case of the reference handbook trying to make things harder than they really are. Opposite charges attract, same charges or similar charges repel, and if you remember that, you'll be clear on the direction. And then one last interesting thing that we can do with this is we can substitute, since we know this relationship between a force and a field, we can rearrange that and say that the field is the force divided by the charge. And then we can divide by either one of these charges. So let's say we divided by Q2, with the idea being that Q2 is creating some field, and then we're introducing Q1 into that area. So then we can say that the field, because now we've divided by Q2 and we're replacing F over Q with E, is equal to only the other charge that remains, and we'll just say that's Q1 over 4 pi permittivity r squared. So this formula would give us the field intensity that results from a point charge. That point charge being Q2 is producing some field, and then Q1 is being introduced. So a few different presentations of the same idea there with forces and fields. And we're going to work more with voltage and current when we get into DC circuits, which will start in the next video. But for now, let's just introduce them. What is voltage really? Voltage is the work required to move a unit of charge from one point to another. Or another term that's often used to describe the voltage is the potential difference. It's the potential to do some work. What work? The work of moving a charge. So you'll hear me use those terms interchangeably, whether I say voltage or potential difference or electrical potential. For DC circuits, you can think about a battery, has a different charge at both terminals. For AC circuits, you can think about a generator, but the idea is the same regardless. In terms of formulas, we really only have one that involves the voltage for electrostatics, and then we'll have more when we get a little bit further. But they use the example of parallel plates. If you have two parallel plates, which have some voltage difference between them, some voltage V across those two terminals, and suppose those plates have a distance between them of D, then there's actually an electrical field between those plates, and we can quantify the strength of that field as E equals voltage over distance, V over D. And let's think about the units of that. The units of voltage are going to be V, and the units of the distance are typically meters. And we said earlier that field could have units of newtons per coulomb or volts per meter. So these are actually the same thing. And for the current typically gets the variable I, and sometimes we'll use capital I, sometimes we'll use lowercase I. The reference handbook is a little bit inconsistent here, but I'm okay with either one. I've seen it both ways in various resources. A technical definition of current is it's the flow of charge, so it's the change in charge per unit time. The way that's introduced in the reference handbook is that current, I as a function of time, t, is equal to dq of t dt. So they're using a calculus strategy to write this. It's the change in charge per unit time. And that's fine, but we're probably not going to use that and come back to a calculus representation of current. For the most part, we'll just use the variable I or capital I. And the units that current has are amps or amperes, but usually we just say amps. And what is an amp? Well, if we said a unit for electrical charge is the coulomb, and it's the change in charge per unit time, then an amp is really a coulomb per second. Other than electrostatics, we won't say coulombs per second, but we may use it in this context. Later on, when we get into DC and AC circuits, we'll use amps exclusively. And I wanted to at least mention magnetic fields. The foundational equation tells us that the magnetic field strength H is equal to the magnetic flux density B divided by the permeability mu. So let's write down what some of these variables are. This is the magnetic flux density, and that has units of teslas, T. And mu is not the permittivity as we had with electric fields, it's the permeability. But it's the same idea. It's the ability of an electric field to exist in a given medium. We call that the permittivity. The ability of a magnetic field to exist in a given medium is the permeability. And that has units of henries per meter. And the result, the magnetic field strength, comes out in amps per meter. So it should be the case that we divide Tesla by Henry over meter, we get amps per meter. I don't know of a way to prove that to be true, but I trust that it's true given this formula and also the units provided in the reference handbook. Again, there's a lot deeper that you could go into each of these ideas and probably quite a bit more foundational information that may be necessary to really get a good handle on electrostatics. But from a high level, these are the heavy hitter equations that you want to be aware of. And when we do some practice problems, there'll be an opportunity to put some of these to work.